Good morning, everybody. Today we are going to discuss the topic defects in solids. Defects in solids. We know solids is made of different crystals. Crystals is made of different types of unit cells. If the crystal is a perfect crystal means the arrangement of particles are in the regular order, in a systematic manner. That is called a perfect crystal. But if arrangement will differ, irregular in arrangement of different particles, this is called defect. Defect in solids is also called imperfection in solids. Imperfection. It is also called imperfection. Called imperfection. Of solid. So this irregularity is called defects. When the defects arises in solids, solid shows different characteristics, different physical behavior, change in conductivity, change in melting point, boiling point, like this. So many physical behavior changes. Generally, defects are two types. These two types defect. One is called point defect. Second one is called line defect. Point defect means irregularity in a particular lattice point. When we observe defect around the lattice point in a particular point, that is called point defects. But line defect means irregularity along the lattice points in a line, either horizontally or vertically. Either horizontally or vertically, the defects observed. This is called your line defect. So, generally, we'll discuss regarding your point defects. These point defects are of different types. What are these? It may be, these point defects generally called as intrinsic defect. It is also called as intrinsic defect. It is of different types. It may be stoichiometric, defect. maybe vacancy defect. Third one is your non-stoichiometric defect. Stoichiometric defect. This stoichiometric defects maybe it is generally observed both in ionic and non-ionic solids. This stoichiometric defect may be a vacancy defect. Vacancy defect means vacancy observed, irregular arrangement observed due to loss of particles from the lattice points. When the particle will be lost, will be removed from the lattice point, that is called vacancy difference. It may be interstitial defect. Interstitial defect means defect observed due to dislocation of particles from the lattice point to the voids. When the particles will be removed from the lattice point to the voids, they occupy in the voids, either in tetrahedral voids or in octahedral voids. This is called your interstitial defect, and this defect also called as dislocation defect. Third one, this defect, this particularly interstitial defect may be observed in case of ionic solids. These are two types. One is Schottky defect. Second one is Franken defect. And these two defects generally observed in case of ionic solids. And your vacancy and interstitial defect generally observed in case of non-ionic solids. So let us discuss these two types of defects. These are very important for your examination. Schottky defect generally observed when both cation and anion. Let us draw the diagram. And this type of defect, Schottky defect, observed in case of ionic compound, observed in case of ionic compound where the size of cation and anion are comparable in size, means are similar. Similar size of cations and anion shows this type of defect. So how the defect? This is not a defect. It is a perfect crystal. This diagram shows a perfect crystal because there is no dislocation, there is no rearrangement. But one thing, if you remove one positive ion here, cation, and one negative ion here, that means same number of cation and anion are missing from the lattice point. Same number of cation and anion missing from the lattice point. Same number of cation and anion missing. And as the cations and anion are missing, so density decreases. So what are the characteristics of these solids? First one is cation and anion missing from the crystal. Same number of cation and anion missing from the crystal. Second, as they are completely removed, density decreases. Completely removed means density decreases. Then, what type of crystal shows? Ionic crystals. Ionic crystals having similar size of cation and anion. Ionic crystals having similar size of cation and anion generally shows this defect. And another importance is crystals having high coordination. Crystals of high coordination number shows this type of defects. And this type of defect generally observed when it will be heated. When the crystal will be heated, then the same number of cation and anion will be removed from the lattice points. And examples are, what are the examples? Examples generally sodium chloride, alkyl metals halides. All alkyl metal halides show these defects. Sodium chloride, potassium chloride, cesium chloride, silver bromide. This type of solids shows Schottky defects. Then second defect is fractal defect. It is also called dislocation defect. Dislocation defect. What are the characteristics? Here, it is observed between in the solids produced by smaller cation and larger anion. Cation will be small, anion will be larger. This is the characteristics. What type of solids? Ionic solids, no doubt, but there is a greater difference, larger difference in size of cation and anion. Generally smaller cation and larger anion solids produce this defect. So you can also mention this one: larger cation, smaller cation and larger anion. Then here, what is the characteristics? The characteristic is where irregularity occurs. This is not an irregularity. This is a perfect crystal. Where it will be imperfect, where it will be a defect, when a smaller cation is missing from lattice point but occupies in the voids. That means it will be removed from the lattice point. Look at here. It will be removed from the lattice point and occupied in the voids. But in Scotty defect, what we observe? Both cation and anion completely removed from the lattice point. But here it will not remove. It will be just dislocation. It will be dislocated. That means just missing from the lattice point and occupied at the voids. This is the main characteristics. So, as no cations and anions are missing, that's why density remains same density. Density remains same. Then what type of crystal shows low coordination number? Low coordination number. Crystals having low coordination number, so this type of defect. Density decreases. Size of cation anion should be differ in size. And due to this defect, due to this irregularity, it shows conductivity, showing electrical conductivity. So examples, what are the examples of this type of defect? Your AgCl, AgI, AgBr. Means transition metal halides. Transition metal halides shows your Frenkel defect, but alkali metal halides, sodium chloride, potassium chloride, this showing Scotty defects. But one question generally, why AgBr is showing both defects, Frenkel defect and Scotty defect? Only difference is because in case of AgBr, the different size of Ag plus size compared to your Br minus, although larger, it is smaller, but it is lies intermediates. Ag plus size is not much smaller, not much bigger. If the size remaining same, that is your Scotty defect. If size will be very less, much more difference. If size difference will be more, that is Frenkel defect. If size remaining same, that is your Scotty defect. But here, Ag plus and Br minus size is just intermediate. Neither more nor smaller. That's why this type of crystal shows Schottky defect and Frankel defect. This is about your stoichiometric defect. But the question is, why these type of crystals are called stoichiometric defect? Why this is called as stoichiometric? Stoichiometric defect means the cation's anion ratio, cation and anion ratio remains same. There is no change in the ratio of cation and anion. Means the simplest ratio remaining same for the crystals, either in solid or in the formula. In both cases, in crystal formula and actual formula remain same. You can write also stoichiometric defect means actual formula and crystal formula remain same. Means ratio of cation and anion remains same. That's why it is called a stoichiometric defect. Then your second type of defect, point defect, is called impurity defect. This is called impurity defect. Second type of point defect is called impurity defect. Impurity defect means we have to add some impurity to the crystals. Means from outside, during formation of crystals, when crystal will be in molten state, we'll add some impurity. Then when it will be solidified, when the crystal will fall, then this type of defect will fall. But what are the characteristics of impurity defect? It is observed when generally it is also observed in case of ionic solids. For example, take a crystal of sodium chloride. Plus minus, plus minus, plus minus. So this is a perfect crystal of sodium chloride. When sodium chloride will be heated, then it will be converted to molten state. When strongly heated, it will be converted to molten liquid form. When with these solids, molten NaCl, when strontium chloride will be added. Look at clearly here, when to the sodium chloride, strontium chloride will be added. It is a perfect crystal of sodium chloride. We are adding impurity SrCl2. Then what happens during heating? During heating, what happens? The position of Na plus, this is Na plus and Cl minus. The position of Na plus will be occupied by strontium 2 plus. Plus, minus, plus, minus, plus, minus, plus, minus, plus. So, suppose take it this Na plus will be removed, occupied by Sr2 plus. In place of Na plus, Sr2 plus will be occupied, then adjacent another Na plus will be removed. Just to see, here Na plus position, here also Na plus position. Both Na plus position, from Na plus position to Na plus ion will be completely removed. 2 Na plus will be completely removed and one place will be occupied by Sr2 plus. Now you see charge remaining same. Your charge remaining same. There is no difference. 2 plus, your 1 plus, your 2 plus and occupied by Sr2 plus. But what is the difference here? In place of Na plus, Sr2 plus is occupied. That's why it is called impurity defect. Because whole crystal is a pure crystal. We are adding SrCl2. That's why Sr2 plus occupied in place of Na plus. That's why it is called impurity defect. Other example, you can take another example. AgCl, you are cadmium chloride. If you add cadmium chloride to AgCl, if you add cadmium chloride to AgCl, then AgCl will show this type of impurity defect. So, question is, what can we use cadmium chloride in place of strontium chloride for NaCl? That's a question. Can we use cadmium chloride in place of strontium chloride for showing this type of defect? No. Answer is no. Because Sr2 plus size is comparable with sodium plus. Here, this type of defect is also a Scotty defect because both are missing. Particles are completely missing. So, here size difference is important because one cation is occupying in place of other. So, size remaining should be same. So, Na plus size and Sr2 plus size is comparable. But cadmium 2 plus will be very small, cannot be fitted with the place of Na plus. That's why we cannot use cadmium chloride as impurity for AgCl for NaCl. Okay, this is called impurity. This is about stoichiometric defect. Then come to non-stoichiometric defect. Non-stoichiometric defect non-stoichiometric defect means differ in ratio of cation and anion. Ratio of cation anion in crystal and actual formula. Crystal formula and actual formula will be different. Means cation anion ratio will not be same. That's why it is called a non-stoichiometric defect. What are the non-stoichiometric? How this type of defect is generally possible? And it is also different types. What are these? Metal excess defect, due to anion vacancy. One type of non-stoichiometric defect is metal excess defect due to anion vacancy. How it will form? Means here irregularity is observed due to missing of cations or anions. It depends upon the nature of crystals. But particularly metal excess defect due to anion vacancy means your anion is missing. When anion is missing and a cation will be excess. That's why it is called metal excess defect due to anion vacancy. Example, you take a sodium crystal, sodium chloride crystals. In sodium chloride crystal, you take sodium chloride and it is heated in presence of sodium vapor. Sodium chloride will be heated in presence of sodium vapor. Then what will happen? When it will be heated, as sodium vapors remain at the surface of crystal, as sodium vapor is available at the surface of sodium chloride crystals, then what happens? Sodium gets converted to sodium plus and releasing electrons. Then this Na+ will be trapped by the crystal on its surface. This Na+ will be trapped in the sodium chloride surface. At the same time, what happens? One Cl- will be missing. One Cl- will be missing, and that Cl- place of Cl- electron remains. What happens? Crystal is heated in presence of sodium vapor. Sodium vapor, due to heating, gets ionized to sodium plus and free electrons. These sodium plus will be trapped by the crystals, and the electron will be remain in the place of Cl-. That's why Cl- is missing, and that place is occupied by electron, and the Na+ will be remain on its surface. That's why it is called metal excess defect due to anion vacancy. And during this, when it will be heated, the color changes to, color becomes yellow. And this yellow color due to electron, excited electron. Due to excited electrons, this was color. Similarly, what are the other examples? Other examples are potassium chloride in potassium vapor gives violet color. Lithium iodide in lithium vapor gives pink color. So you see, color is changing depends upon the energy required for the excitation of electrons. For sodium chloride color is yellow, potassium chloride color is violet, lithium chloride color is pink, because due to difference in size. Sodium, potassium and lithium, due to difference in size, the amount of energy required are different. That's why they show different color. And this type of defect is called metal excess defect due to anion vacancy. Here anion is missing, and that place is occupied by electron. This is the main point. Then second type of defect is metal excess defect. Metal excess defect due to metal excess defect due to extra cations. Due to extra cation. Mainly we have to see what is the irregularity. Here irregularity is excess of metal cations. From where? Due to observing some extra cation. How it is formed. For example, you take one example, zinc oxide. When zinc oxide gets heated, already I have told you, crystal shows defect due to change in physical behavior. If when it will heated, then show behavior, different behavior. That's why it is showing defect. When zinc oxide is heated, then zinc oxide becomes zinc ion and oxygen gas and 2 electrons. Zinc oxide is a covalent nature, it is not ionic. When it is heated, it produces Zn2 plus and half oxygen and 2 electrons to balance it. Anyway, when zinc ion is formed during heating of zinc oxide, this zinc ion occupies in the interstitial sites. This zinc ion occupies in the voids and the electron occupies in the neighboring sites. Zinc ion occupies in one sites and the neighboring sites is occupied by electrons. So when electron will be trapped in the crystal and due to heating, this shows color due to excitation. So this defect observed due to formation of free zinc ions. These free zinc ions produced from the crystal of as is very small size goes to interstitial sites in the voids. It goes to voids. It occupies the voids and the neighboring lattice cell occupied by electron. So due to trap of electron and due to heating, this shows color. What color changes when zinc oxide is heated? Zinc oxide is white, but when it is heated, it becomes yellow. When it is heated, it becomes yellow. When it will be again cooling, again white. When it will heated, yellow, and when it will cool, it will be when yellow when hot and white when cold. Yellow when hot and white when cold. So this type of defect is called metal excess defect due to extra cations. Then another defect that is metal deficiency defect. Metal deficiency defect due to cation vacancy. Cation vacancy. And it is observed in case of oxides of transition metals. Oxides of mainly transition metals, iron oxides, nickel oxides, chromium oxides, like this. But when it shows a defect, the formula changes. already I have told you, it is a non-stoichiometric defect. As non-stoichiometric defect, the formula of iron oxide is a ferroxide, but formula will be metal deficiency defect due to cation vacancy. Correct. It is metal deficiency defect due to cation vacancy. Also, it can be written as due to formation of oxidation of metal ions. How it is will be formed, we will discuss. So, formula FeO will be 0.940, nickel oxide 0.980, like this. So, formula changes. How it will be formed? So, it is a defect. When it shows defect, the formula changes. For example, I will give here. This is the formula of iron oxides. +2, -2, +2, -2, +2, -2. Like this. But when this defect observed, metal deficiency defect. Metal deficiency means what happens? One particular ion will be removed. How it will be removed? Now when this ion will be oxidized to ferric ion. Now the ferrous ion oxidized to ferric ion. So the ferrous ion will not be available here. Now it will be converted to ferric ion. So metal deficiency, why it is called metal deficiency? The particular ion will be not available in the crystal. Ferrous convert to ferric, +3. When it convert to +3, then losing electron, it lose electron, then electron will occupy in the neighboring sides. In the neighboring sides, nearby sides, the electron will be occupied. That's why this defect is observed when the particular metal ion gets oxidized to higher oxidation state. That's why transition metal oxide shows this defect. Transition metal oxides shows this type of defect. Iron oxide, chromium oxides, nickel oxides, so many. So that the formula will be different. So this is about the types of defect in solids